And um, okay, so yesterday we started looking at these rate laws, and are you guys okay identifying it as second order? Feel pretty good about looking at a graph?
Kinda, yeah.
Okay. So again, these will be at the end of the chapter summaries, but knowing the what's linear and how that corresponds to first, second, or zeroth order is important. Okay, so we got to part B yesterday. We wrote the rate law. Which, again, if it's second order, all that means is the exponent's 2. So then we get to the tricky part. It says consider two possible mechanisms. This is the last question C. Two possible mechanisms. And again, a mechanism is like step-by-step process of how the reaction actually occurs. So just a reminder, when you add any set of steps up, what should it always sum, or what should it always add to?
The original reaction.
The original reaction. So, okay, you could do a quick double check. You should end up with 2 nitrogen dioxides on the left, 2 nitrogen monoxides on the right, and 1 oxygen on the right. So here in reaction mechanism 1, you guys see how on the left I end up with 2 NO2s. Okay. Also comparing it to the right, the NO3s cancel, and just do you remember in a mechanism what is the name of something that just is present for one step but not present at the end?
Spectator.
Not quite. Spectator doesn't do anything. This actually does something. It just doesn't. You can't see it at the beginning and the end.
Oh wait, it's
something in the middle. It's called a
mediator.
Close, intermediate.
Oh, there
Okay.
it is.
Okay. So yeah, that would be something. Again, I'm just dropping these words. They would have been really important in the multiple choice, but they will make you sound more credible when you're answering your free response. If you're like, oh, if they say, what role does NO3 play and justify? You could say NO3 is an intermediate because it's not present at the beginning or the end of the reaction. It's just present in the middle. Okay, and so it does add up correctly. So they're saying, is the rate law that I have in the box, is it consistent with this mechanism? So here's the other piece of information they give you. And you're always going to justify your rate law with which step? I know we've cut. I know that. Sorry. Yeah, the slow one. So again, I'm not saying that you guys. I feel like every time I'm reviewing this, because you knew it at one point. I'm not trying to reteach it. I'm just trying to recall, because you're gonna have to quickly recall stuff during that test. So you look at the slow step just by default. You just everything else goes out the door. You're like slow step. And you're like, okay, if these two things are in the reactants, this is called a bimolecular process. Bimolecular because because there's 2 things that have to hit. So question is the rate law that I have in the box, is it consistent with the slow step?
Yes.
So you'd say yes, bimolecular, or you could say 2 molecules of NO2 must collide. Okay, so that first mechanism works. Okay, the second one, part II, it says, is the rate law described by mechanism 2, shown below, is it also consistent with the rate law that you wrote in part B? Justify your answer. So you're going to look at the slow step, and you're like, okay, what is this one? Is it unimolecular, bimolecular, or termolecular?
It's unimolecular.
It's unimolecular. You just look at what has to hit, and you're like, oh, well, this one looks like the rate looks like K step 2 times N2O4, and since it's unimolecular, you'd say, oh, that looks like it's first order in N2O4, and you're like, well, that doesn't match what's up in the box. So that's where they try and get you, but you quickly realize that N2O4 is a intermediate, right? Does that make sense? You can't have, here by definition, you can't have intermediates in any proposed mechanism. You can only have like reactants. So you gotta simplify it down. So you look up, after you've realized that that's an intermediate, you go to this step that also includes N2O4. And since they drew the arrows equal, what can you say is true about the rate of reaction in the forward and reverse directions? Those arrows are the same size. So what's true about the forward reaction and the reverse reaction? They're in equilibrium, so they're happening at the same rate. So what you do is you write a rate law for both directions. So in the forward direction, it would be Kf times NO2 to the second, because this is bimolecular. And then in the reverse direction, K reverse times N2O4 to the first, because this is unimolecular. And then you do a little solving and substitution. So what I need to do, I need to eventually substitute something right there, and I now have this equation. So to get N2O4 by itself, I would divide by Kr. Okay, these cancel. And then you guys okay that I could substitute right there? I'm going to plug all this stuff in for N2O4. So my final rate law ends up being rate equals K2 times Kf over Kr times NO2 squared. Okay, so, and you look at all this, and this is called a lumped constant, and a lumped constant is just a constant, so that equals K NO2 squared, which, is it consistent with our data? Yeah, because it matches that second order data. So actually both of these, this is kind of a good question, both of those are valid mechanisms, okay? And yeah, both are valid mechanisms, and then it would take further studies to figure out which one's really true, but both of them work. And scientists can't really study intermediates because they're usually not present for long enough to actually sense or detect. So this is kind of a theoretical thing. Again, I don't think they're going to ask a mechanism question with only two questions in the thing, but that's it. I would say this is the most fuzzy of all the stuff that we taught this year, was mechanisms and some of the rate laws. I remember this was the lab, if you think back, this was the iodine clock lab, which was exceedingly hard to process because, I mean, it was a lot of data crunching and things magically popping out in equations. So it's the most, I'd say it's the highest level stuff we covered. Had we covered batteries and things at the end, I think that's a little trickier, but this is probably the most algebra and weird conceptual. Okay, mechanisms, I think maybe the week before the test, we'll do a couple more mechanisms problems and try and solidify it. We'll see how many else pop up on the other tests. I'm trying to think, if we cover 2 questions a day, and we have about 4 weeks, maybe five weeks till the test, and we cover 2 questions a day, let's say 4 days a week. We might not do every day. 4 days a week times 5 weeks, 20 times 2 questions. We could go through 40 questions potentially. So, okay. Yeah, I'm going to move to 2018, and I will. Did you guys have a chance? Was there anybody who didn't print it or look at it yet?
I did not.
Okay, well then I will make sure to read the questions slower, and we'll try and just do as much. This is a long question, so we'll try and work through question 1 today. And again, I have to leave at 10 on the dot, so we'll just go. So okay, here's a big long reaction. It says, student performs an experiment. They're going to determine the value of the enthalpy change, delta H reaction, for the oxidation reduction reaction represented by the balanced equation above. Okay, it says determine the oxidation number of Cl in NaOCl, which is, I think, sodium hypochlorite. So, I know I didn't have you guys memorize all the ions, but let me switch over to my screen. Control Alt Screen. Okay, and let's just look up OCl minus, ion. So hypochlorite is OCl minus, okay? And it's weird that they wrote it this way because usually most chemists write it ClO minus, and that's how it was on our orange ion sheet last year and everything. So let me go back to my whiteboard. And come in here. So it says OCl minus is paired with a Na plus, and it wants you to determine what is the oxidation state of that. Not the O, the Cl. Okay, so oxidation states are the weird ones. Do you guys remember by default there was two elements, O and H, that always have given oxidation states? Do you remember the oxidation state of O?
0, right?
No, O2. O2 would be 0 because it's in its pure elemental form.
Oh, okay. Then that one's. God, I'm gonna guess 1.
Hydrogen, we'll just say that Keaton was talking about that, has an oxidation state of +1 in like 95% of the cases. Oxygen has an oxidation state of -2 in 99.9% of cases.
So is it?
Yeah, go ahead.
Is it like the same as the electron charge?
It's
like
very
usually
in most cases.
Except for like transition metals
Except for
and some
this, except for this one. No.
levels,
Yeah, except for like this one. This is called lithium hydride, and in this case, hydrogen has an oxidation state of -1, and lithium has an oxidation state of +1. Usually, hydrogen is a +1, but there's some exceptions. It's just weird, okay?
I don't even have -1.
In this case, what it was, lithium, which usually has one valence electron, right?
Mm-hmm.
And hydrogen also has one. It turns out hydrogen is more electronegative, and it ends up doing this, Li plus, H minus, because now hydrogen has its full valence shell with two. You can watch another.
That actually makes sense.
Yeah, and so hey, what we say is this -1 is showing you that it basically has an extra electron, and it's been reduced. Okay, reduced.
Yeah.
Yeah.
That actually makes a lot of sense in lithium.
Yeah, and correct. Like this one, hey, HCl, which is hydrochloric acid. Hydrochloric acid, its Lewis structure looks something like this, right? Now, hydrogen, which usually has one valence electron, it's kind of given it to chlorine so that it can complete this. So hydrogen here is a +1, and chlorine here is a -1. Those are the oxidation states. Yeah.
So why doesn't like let's say we put sodium and hydrogen together, right?
Yep.
Since sodium also has one valence electron, why doesn't does sodium give its valence electron to hydrogen?
Yeah.
Due to the fact that
so this
hydrogen
would so like NaH is sodium hydride. That's what, like, yeah, when you hear the term hydride,
that's something that's hydrogen, right?
Yeah, but it also means that the hydrogen has gained an electron, that it's basically got a -1 oxidation state.
Versus, I'm guessing that only happen with these rare elements, right?
It can only happen with the alkali metals. Correct. And I shouldn't say that. I think there might be aluminum hydride. Let me switch back over, and I'll just Control Alt Screen. Let's just look up. I think, if I remember right, aluminum.
Let me look. Oh yeah. Wait, no. Aluminum has 2 valence electrons. That'd be
No. Hold on. But you guys, so can you see my screen on Wikipedia?
Yeah, I can. Yeah.
So it says aluminum hydride, also known as alane, is an inorganic compound with the formula AlH3. Okay.
Okay.
And it's probably, I would think it's unstable. Anyways, it's not a common chemical, but here the hydrogen has a oxidation state of -1. But in every other like acid or every other compound like methane,
Yeah.
it turns out the oxidation state of hydrogens in methane is going to be +1. So if you have 4 +1s and methane is neutral, what's the oxidation state of the carbon?
-4.
-4. Yeah, -4. So
Okay.
yeah, it's weird. The central atom in this one has a minus oxidation state, and it's a covalent molecule. And the aluminum hydride is an ionic crystal, and the aluminum has the positive charge, and the hydrogen has the negative charge. Okay. So, anyways, it's but in most, let me go back. In most cases, hydrogen is a +1. Okay, and oxygen is a -2. So that being said, that's where you always start. You're going to be like, okay, this is a -2. The sodium, okay, the sodium by default is going to be its charge. Alkali metals are usually a +1. So then it's saying, what does the Cl oxidation state have to be? And it says NaOCl. It says it's neutral. So what's the Cl have to be?
The Cl has to be +1.
Yeah, it has to be a +1, which is weird because usually,
it is weird.
Yeah, usually what's chlorine?
-1.
A
right?
-1.
Yeah.
Usually, okay, and so this is actually called sodium hypochlorite. This is what's in bleach. So it's a really really nasty chemical because the chlorine really wants electrons. And it'll find electrons from a lot of things, which is why it's a good cleaner, right? Bleach is a good cleaner and sanitizer because that chloride is really oxidized. It does not like being oxidized. Okay.
So it'll just take up all the stuff.
It'll take up all the electrons it can, and it does that by attacking any other chemical it can find. Right?
Oh God, very volatile.
Okay, so calculate the number of grams of Na2S2O3 needed to prepare 100 milliliters of 0.5 molar Na2SO3. So this one,
right. That's just a molarity.
Yeah, that's just a molarity thing, right? So let's just review. You need molarity is always equal to moles over volume, right?
Mm-hmm.
You need 0.500 molar. And we need to figure out how many moles, and we need 100 milliliters. What's 100 milliliters in liters?
0.1.
0.1. There you go. There you go. So all you're going to do, first of all, is solve for n. So I multiply this up. I end up getting 0.0500 moles. And then it says calculate the number of grams. So you're going to multiply by the molar weight, right?
Yes.
Molecular weight. So, and I wrote this out. So it ends up being 158.1. So you take 0.05 moles times 158.1 grams per mole. And they say it comes out to 7.9 grams. Okay, let me scoot.
When do they only use 2 sig figs?
Sorry, 7.90. It should be 3. Thank you. Good catch. And again, you just know that because that one has 3.
Because the starting has 0.50.
Yep. So 7.90. Okay. In the experiment, a student uses the solutions below shown in the table. Okay, and so they gave a table. What are they doing? Well, I don't understand what they're doing. Are they just going to mix it?
Solutions. It's the different solutions that he has that he's done.
Okay. Using
and then it asks,
Oh, it's asking for limiting reactant, right?
I think so.
Okay.
Yeah.
Okay. So okay, so really properly you would convert these to 0.005 liters, 0.005 liters, 0.005 liters. And you could multiply the concentration times the volume to figure out moles. If you multiply these two quantities, you get moles, right?
Yeah.
But here's how I would justify it so you don't have to calculate, right? What's true about all the volumes?
They're the same.
They're the same. What's true about all the concentrations?
Also,
They're the same. So aren't all the moles constant or the same across the board?
they are.
So then how are you going to determine the limiting reactant?
Don't you look at
The equation.
stoichiometry?
Yeah.
Whichever one has the
So which one's going to run out first?
The Na2S2.
Careful. Which one has the biggest coefficient?
NaOCl.
Oh.
So what this one is, it's getting used. It's getting used up 4 times as fast as this one, right? And then compared to the sodium hydroxide, how much faster is it getting consumed?
So it's getting consumed half as fast as that one.
Yeah.
Of the NaOCl, but twice as fast as the Na2S2O3.
Yeah, so this guy and the NaOCl is getting used up twice as fast as the NaOH, right? Because of 4 to 2 ratio. So you could just, instead of multiplying and doing all this, you could just say, since the concentrations and volumes are equal, you would say NaOCl has to limit the reaction because of the biggest coefficient. Okay. I'm doing a time check. I got 7 minutes. Okay, we'll see if we can do this. Here's a graph. It says the solutions are all originally at 20 degrees Celsius. So all 3 of those things are combined in an insulated calorimeter. The temperature of the reaction mixture is monitored as shown in the graph below. According to the graph, what is the temperature change of the reaction? You guys would take a stab at it.
32.3 divided or minus 20.
Very good. Which would be 12.3 degrees Celsius, which is delta T.
It would be 12.7.
Can I not? No, 32.3 minus 20 is 12.3, right?
Yes.
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 Yep. Okay. Very good. That would be a nice question. That would be a really nice question to get on the AP test.
It's all just like that, like 50 times.
Oh,
okay.
Wow.
E says the mass of the reaction mixture inside the calorimeter is 15.21 grams. Okay, so calculate the magnitude of the heat energy in joules released during the reaction. You guys remember the heat equation? We mentioned it a couple days ago, I think.
MCAT.
Yep, MCAT. And you can just use 15.21 grams times, they say the heat capacity of the solution is 3.94 joules per gram degree C, times your change in temperature, which is 12.3 degrees Celsius. And I have the answer, so let me figure out what they said. They actually used 12.5 in their thing. I think 12.3 would be valid. They wouldn't count it wrong, so let's say it comes out to... Let's say it comes...
12.5.
Well, let me look at my picture. Well, they said that line ends right in the middle.
Oh, okay. I see.
But that's okay. So they got 749, which we would be close. You wouldn't be marked down for that. 749 joules of energy. Okay, and that was the heat absorbed by the calorimeter. No, it says assume that the heat absorbed by the calorimeter is negligible. So we just released, let's see, 749 joules. Okay, we haven't calculated delta H yet. This is just how much energy was released. And you'll notice, because we know it's exothermic, eventually when we calculate delta H, what's going to be true about the sign?
It's going to be flipped.
It's going to be flipped. It's going to be negative. Okay. So using the balanced equation for the oxidation, reduction, reaction, and your answer to part C, calculate the value of the enthalpy change, delta H in kilojoules per mole. Okay. So, and this is per mole of reaction. Okay, include the appropriate algebraic sign with your answer. So I think it makes most use. Let me double check that I'm going to do it right. Yep. Okay. It makes most sense to use the limiting reactant because that's what basically stopped. That's what stopped it from heating up more. Does that make sense? As soon as you mixed all three together, okay, they combined, and as soon as it stopped, the energy stopped being released, and that's why we petered out, right? Had we had more of that reactant, we would have reached a higher final temperature. So what you have to do is you have to use your moles, which actually I think we calculated moles, right? In the very first part. How many moles did we get? Oh, we got 7.9 grams. We had this many moles, right?
Yes.
Was that the limiting reactant? Yeah, NaOCl.
Mm-hmm.
Yeah.
I think so.
Okay.
That's it.
Oh, thanks, Linus. You can keep watching. Oh my goodness, Linus is gonna watch too much TV with all these meetings. Okay, so hey, what you do is you'd take 749 joules, divided by the moles of the limiting reactant. Okay, and wait, what? Oh wait, but that was for 100 milliliters. Oh geesh, I don't know why they tried to mix this up. We didn't use 100 milliliters.
No,
we need to calculate a new number of moles. We used 5 milliliters, which would be 0.005 liters times 0.5 moles per liter, because it was 0.5 molar, which comes out to half of 0.005 is 0.025 moles.
Yeah, 2 minutes.
Okay, I got 2 minutes. That many moles. Okay, and then they took that many moles and they use the stoichiometric coefficient. Okay, so here's just by default delta H. Oh geez, I can't keep scrolling. Delta H is equal to it's always equal to the heat released or absorbed. I'll say heat change.
Okay, so like that would be the joules we got in the last equation?
Yep, divided by the moles of the limiting reactant. But then you also have to reactant. You also have to account for this 1 over the stoichiometric coefficient. I don't know how to write. Let's see, what's a good variable for stoichiometric coefficient?
Would it just be like a to the power or something?
I'll call it this. I'll call it this, and we'll call the moles of limiting reactant Na. Because they want it in per reaction, or per moles of reaction. So what you have to do is you have to count for the stoichiometry. So here you go. Because I'm rushing through 749. We reacted this many moles of limiting reactant, and the stoichiometric coefficient for that reactant was 4. Was 4. So you have to divide it by 4 if that's what you're basing your answer on. So
if like for one whole of the reaction to take place.
Correct.
Basically.
For one molar quantity or for one full reaction to take place.
Reaction quantity.
Yeah, you got to account for that. So I don't think they would. I think you'd get most of the credit if you just did this. If you forget about the stoichiometric coefficient, then they're going to take off at least 1 point. Okay, and so I think they would probably be. I think they got yelled at, if I remember right, because they didn't necessarily specify. I guess they said molar reaction, but they made it pretty convoluted. So I think they would say for NaOCl, or they would tell you the chemical species, how many kilojoules of energy were released. Calculate delta H, and then you'd know you'd basically just have to do this quantity. But in their answer key this time in 2018, they did divide by 4 at the end, and they got they also, there you go, made to make sure to do this to flip the sign because I'm going too fast, and they ended up with what does it come out to? Negative 120 Yeah, there you go. Joules per mole reaction, which is equal to negative 1.200 or 1.20 is how they wrote it. Times, what do I get? 10 to the, no, okay, I can't read. That comes out much bigger. Like 1.20. I gotta calculate it before I forget. Let me pull up my calculator. Or okay, I'm already running out of time. It comes out big. It comes out big. It comes out in I can do
negative
this.
big actually. So it actually comes out very small.
I can do this. 1, 2.
No, make negative big.
1, 2, 3. 1, 2, 3. I think it comes out to this joules per mole. Okay, and then changing that to kilojoules, divide by 1,000 kilojoules per mole. You end up with 1,200 kilojoules per mole, which is a huge, huge reaction. So
negative.
Yeah, negative. Thanks.
Yeah.
So
Yeah.
okay.
Yeah.
Hey, I apologize. I gotta run. What I'll do, I'll be better. Let's finish. We'll finish this question and do number 2 tomorrow.
Oh.
And I'll be on as of now back at 10 o'clock. So let's say 10 o'clock tomorrow. And since tomorrow is Friday, right?
Yeah.
I'm gonna let's start with questions. So if you guys are reviewing and just have general questions, let's spend 15 minutes where we can just talk. And let's do 15 minutes of questions, 5 minutes of what your weekend plans are, and then 10 minutes of trying to finish number 1.
Huh.
Yeah. So that we're so we're not
You're
rushing.
going to run with the track, aren't you?
I'm gonna do what?
Are you running with the track this morning?
The track? What do you mean?
My friend Ryan Clark invited me to come run with him this morning.
Oh no, I have to go meet with Mr. England, but that sounds fun. Hopefully they're staying away from each other.
Oh, by the way,
6 feet apart.
By the way, Keaton, Savannah, Evan, congratulations on graduating.
Thank you.
Yeah.
Thank you.
Yeah.
Arthur,
Okay.
do you have all your classes passed?
See you guys later. I'm gonna hang up.
All right. See ya.
All right. Bye.
Yes.
Hey John, just a second. I'll get my camera up.
Okay.